Hello everybody, welcome back to the second part of Lecture 2. And today we will introduce an alternative sorting algorithm, merge sort. Merge sort uses a divide and conquer approach, which is a very commonly used approach for the design of a lot of algorithms, as we will introduce in future lectures. And today we will see the pseudocode implementation of merge sort, and we will analyze its running time and then compare it with the insertion sort algorithm that we covered on Tuesday. So what is this alternative divide and conquer approach to sorting problems? So according to its definition, divide and conquer is an approach that breaks the problem into several subproblems that are similar to the original problem, but smaller in size. And then we solve the subproblems recursively, and finally combine those results to create a solution to the original problem. And this approach involves 3 steps. Okay, so here we mentioned the recursive algorithm. The term recursive means that when we solve a problem, they call themselves one or more times. So the divide and conquer paradigm involves 3 steps. The first step is divide. We divide the problem into a number of subproblems, which are smaller instances of the same problem. And the second step is to conquer the subproblems by solving them recursively. By that we mean further divide the problems, or when the size of the subproblem is small enough, we just solve it in a straightforward manner. And the last step is combine. We combine the solutions to all the subproblems into one solution for the very original problem. And the merge sort that we're gonna introduce here is an example of a divide and conquer algorithm for sorting problems. And as we will see, it turns out that a merge sort, the worst case running time of merge sort is much less than insertion sort. That means it runs much faster on average than insertion sort. Let's look at merge sort. So in the language of the 3 steps of divide and conquer, the first step is to divide the n element sequence to be sorted into 2 subsequences of n over 2 elements each. Okay, we divide the input sequence in half. And the second step is to conquer. We sort the 2 subsequences recursively using the merge sort procedure. Okay, so this is a recursive call of the merge sort function itself. And the third step is to combine. We merge the 2 sorted subsequences to produce the sorted answer to the original problem. Okay. Therefore, and the detail about the recursion is that the recursion reaches the bottom when the sequence to be sorted has just one element in it. It has length 1. So in this case, there's no work to be done. We don't need to do anything about an input sequence of length 1. And of course, the key operation involved here is the merging of 2 sorted sequences in this third combine step. So how do we merge 2 already sorted sequences into one sorted sequence? That is the key operation that we're gonna introduce first. Okay, so we need to merge by calling an auxiliary procedure named merge. So this is a procedure that we need to implement first before we implement the complete merge sort. We need to first have a merge that merge procedure that does the combine step for us. So this procedure takes 4 input arguments. The first one is A, and it's a input array, and P, Q, R are the indices in such an order that P is always smaller or equal to Q, and Q is always smaller than R. So that means Q is in the middle between P and R, and P is the smaller index, and R is the larger index. Q is in between. So we assume that the subarrays A from P to Q and the right subarray A from Q plus 1 to R are already in sorted order. So that's our assumption. So we basically divide the input array into 2 halves, and we assume that the 2 halves are already solved in sorted order. And then this merge procedure will merge the 2 subarrays to form a single sorted subarray to replace the current subarray A from P to R. So this is basically an in-place operation. It merges the subarray on the left and on the right to give an outcome that replaces the original input array A. Before we see the implementation of merge procedure, let's take a look at what this procedure does using the playing cards analogy that we used before. So imagine we have 2 already sorted piles of cards as inputs, and each with smallest cards on top. And we wish to merge the 2 piles into a single sorted output pile. So the strategy that we can take is to choose the smaller of the 2 cards on top of each pile and place it onto the output pile. And we repeat this step until one input pile is empty, and we just append the rest of the other pile to the output pile, and then we will have a output pile that's in sorted order. Okay. So each basic step is just comparing two cards on top of each input pile. So it takes constant time. And in total, we perform at most n basic steps. And here n is the total number of the input cards. So the merging will just take theta n time. And I hope you still remember the theta notation that we used to describe the order of a function. So here the running time for this merging step is a linear time function. So here is a little demo of the playing card analogy that I just described. So imagine we have 2 input piles of cards, and each of them is already in sorted order. And the black one is 1, 3, 5, and the red one is 2, 4, 6, 8. So the strategy is that we take the 2 of the top cards and compare them. So here we have 2 and 1, and we take the smallest, right? Because 1 is smaller. We just take 1 out and place it in an output pile. Okay. And then what's left is on top is 2 and 3. And again, we take the smaller. So this time we take 2, and we append this card to the output. Here, next we have 3 and 4. We take whatever is smaller. We take 3, and the top is 5 and 4. We take smaller, so this time we take 4. And here, the 5 is the only one left in one pile, so we take 5. So at this point, the input 1 pile is already empty, so we take what's remaining in the next in the second pile and append them to the output. And after we've done this, let's look at our output pile. So they are already in sorted order. So this is the results of merging two sorted piles of cards as inputs. Okay, hopefully you can see them clearly. Okay. It's terrible to make them show correctly. Okay, as you can see. Oh, where's the 1? Okay, it's hiding here. 1, 2, 3, 4, 5, 6, 8. So this is the basic procedure of merge. Basic steps of procedure. The merge procedure. Now let's look at the pseudocode implementation of merge sort. Here is the code. It's a lot, but don't worry too much. If you take a closer look there, you will find that they are not scary at all. Okay, so here is how we demonstrate the input array. We have A, we have several cells indicate the values, the elements in A, and we have the starting index P, the ending index R, and Q in the middle of it. And we also show Q plus 1 just for clarification. So let's look at the first line and the second line. They compute the length for the subarrays, and the subarray on the left ranges from P to Q. So it computes the length N1 by Q minus P plus 1 and assigns it to N1. And the length of the subarray on the right is R minus Q, right? And assigns it to N2. So, and on line 3, it creates two new arrays to store the two subarrays. Okay, but with one more additional elements, right? So the length for the left for L, for the array L, is N1 plus 1, and the length for R, for the subarray R, for new array R, is N2 plus 1. And you will see why we need one additional element for the two arrays. And here's the new array L and R. So from line 4, next from line 4 to line 7, we just copy the original elements in A to R, right? We just copy the elements from AQ, from AP to AQ to L, and the elements from AQ plus 1 to AR to R. And line 8, from line 8 and line 9, we just append to sentinel value infinity, right, at the end of each new array L and R. So these two sentinel value are just for easier comparison when we carry out later steps. So the infinity is always larger than any values possible in the input array A. So by having this infinity at the end of L and R, we can avoid the operation of checking whether each array L or R is empty in each basic steps, right? Because when we made a comparison in line 13 and line 16, whenever it reaches the end of L or R, the ending infinity is always larger than whatever is left in the other array. Okay, it's just a technique for convenience. Okay, and the key merging operation happens from line 12 to line 17. So first, before that, we need to reassign reinitialize I and J to 1. And from line 12 to line 17, we let K iterate from P to R. So that is the iteration over all elements in A, over all indices in A. Okay, and if the top elements in L is smaller than the top element in R, then we copy the smaller elements back to the corresponding position in A, and then we increment the index I by 1, because I is the index of the array L, right? And if it's the other case, if the smaller one is in R, then we copy the elements in R back to the corresponding position in AK, and then we increment the index in R, which is J, by 1. Right? So in total, we will perform R minus P plus 1 basic steps, which is the length of the original input. Right? We just need to perform that many basic steps of comparison and copy to merge all the sorted results back to the input array itself. And later we'll see a step-by-step example of how this pseudocode of merge procedure works. Now let's go over the merge procedure step by step, with an emphasis on where the merging operations happens from line 10 to line 17. So assume our input array A is like this. It has 8 elements, and the index start from P equals 9 and ends at R equals 16. And our split is at Q equals 12 here. So after everything from line 1 to line 9, we have already created a new 2 new subarrays in L and R, and we have copied the elements from AP to AQ to L, and AQ plus 1 to AR to R, and we have appended the sentinel elements infinity at the end of L and R, and have already initialized I and J to 1. Okay, so after the first step of iteration k equals 1, so we find that R1 is smaller than L1, right? And that's why we copied R1 to A1, and then we increment the index in R, which is J, by 1, and now J is 2. J points to the second element of R, and I is not changed. Okay, so please note that we colored the already compared and copied elements in L and R in dark gray, and the already sorted elements in A as in dark gray, and the unsorted parts in A in dark color. Okay, so the next step, we need to compare the top elements in R and L again, which is 2 and 2, because they are equal. So according to how we arrange the if and else the statements, we just copied L1 to A2 and increment J, increment this time I by 1. Okay, so this is the first step of the merging operations. And now we can examine all the following steps in a similar way. So we just copy the smaller elements in R or L, copy it back to A. So this time the smaller one is in R, and after that we'll increment J by 1, and next the smaller one appears in L, which is 4. So after copying 4 back to the position where k is, we increment I by 1. And like this, and so on and on until we reach, finally, maybe at the next page, we'll reach, after we copy the smaller one in R here, after we copying back 6 back to k, then we increment j by 1, then we'll reach the sentinel element in R, which is infinity, and infinity is larger than any elements, any numbers. So in the next page, we will have j reaches the infinity, and because the current elements in Li is 7, and we just copy 7 back to A. So, and L also reached the infinity elements. So until this step, everything in L and R are already compared and copied back to A. So that means at these points, all elements from AP to AR is in sorted order. And we have successfully merged the already sorted elements in L and R back to A, so that the whole sequence A is in sorted order. Though the implementation of merge procedure is quite straightforward, and it's easy to tell that it is correct after we have gone through the merge procedure step by step, it still doesn't hurt to check its correctness formally using the loop invariant method, as we did for the insertion sort. So a loop invariant for the merge procedure is that at the start of each iteration, the subarray from AP to k-1 contains the k-p smallest elements from L and R in sorted order. And the current top elements Li and Rj are the smallest elements of their arrays that have not been copied back into A. And in order to check the correctness of the loop invariant, we need to analyze, if we remember, we need to analyze first the initialization condition, that is prior to the first iteration, that is k equals p, right? So we just emphasize the line 12 to line 17 here, because this is the loop that we want to check the correctness. Okay, so prior to the first iteration, the array, subarray A from P to k-1 is empty. It contains 0 smallest elements from L and R. And since the initial condition of the initial value for I and J is 1, therefore L1 and R1 are the smallest elements. So it means that the initialization condition is satisfied for loop invariants. And next, we need to check the maintenance condition. That is, suppose that suppose the Li is smaller than Rj, and then Li is the smallest element that has not yet been copied back, right? And because AP A from P to k-1 contains k-p smallest elements, and after line 14, because Li is smaller than Rj, the condition, the line 14 is executed. After we copying Li back to AK, then this time, after that, the subarray A from P to K will contain k-p plus 1, right? Because we copied one more element back. It will contain k-p plus 1 smallest elements. And increments k and I will reestablish the loop invariant for the next iteration. Okay, so the maintenance condition is also satisfied. And lastly, we need to, and also before we end, if Li is larger than Rj, then same analysis can apply, right? And lastly, we need to analyze the termination condition. which is after the for loop terminates, then k is r plus 1. And now the subarray a from p to k minus 1 is a from p to r if we replace k back to this expression. So this array contains r minus p plus 1 smallest element, which is all the elements in A, right? In sorted order. And L and R together, they contain r minus p plus 3 elements because we need to consider the last two, the sentinel elements infinity. But the last two largest sentinel values have been, all but the last two largest sentinel values have been already copied back. Therefore, the termination condition also satisfied. So this is how we formally check the correctness of the merge procedure, especially for the for loop from line 12 to line 17. Next, let's analyze the running time of this merge procedure. So this is very important for our later analysis for the merge sort procedure. Okay, so let's look at the conclusion first. So this procedure takes time theta n, which means it runs in linear time. And here n is r minus p plus 1, and it's the total number of elements being merged. And let's break down the pseudocode again to see why this is the case. Okay, so from line 1 to line 3, we just compute n1 and n2 and create two new arrays. So these three lines takes constant time. There's no loops involved, right? And also from line 8 to line 11, it's also assignments of values. So they just take constant time too. And then let's look at the first part, the first for loops from line 4 to line 7. So from line 4 to line 5, it's a for loop iterates from 1 to n1, and 6 to 7 is a for loop iterates from 1 to n2, and in total it takes n1 plus n2 time, and n1 and plus n2 is the total number of elements. Therefore, the total time is theta of n, right? And lastly, from line 12 to line 17, k iterates from p to r, which also has n iterations, right? And within each iteration is just an if and else statement. There's no inner for loops involved. So that is to say, the long for loop also takes constant time, also takes linear time, theta of n. So altogether, we have two, considering all the for loops together, they will take a theta of n times. Therefore, the running time of merge procedure is in linear time. In other words, it's quite fast. After we have implemented the merge procedure, we can now use this procedure as a subroutine to implement the merge sort procedure. So here is the pseudocode for the merge sort procedure. As you can see, it sorts elements in the subarray from A of P to AR. And if P equals R, then this procedure does nothing, because P equals R means that there is just one element in A, and it's therefore already sorted. So if P is smaller, strictly smaller than R, then in the if condition, we will first split the input array into two subarrays, A of P to A of Q, and AQ plus 1 to AR. And each of them contains n over 2 items. And then we recursively call merge sort on each subarray. After the recursive call of the procedure itself, we merge the results by calling the merge procedure, which we just defined. So this is the implementation for merge sort. And because this procedure takes 3 arguments as its inputs, an episode of an subarray A, which starts from the index P and ends with index R. So if we want to sort the entire sequence A ranges from, for example, 1 to n, then we just make the initial call like this: merge sort A from 1 to the length of A. In the language of divide and conquer approach, then this line 2, is the divide step. It computes the midpoint of the input sequence. And line 3 and line 4 is the conquer step, because it's solve the subproblems by calling the function, by calling the merge sort procedure itself recursively. And line 5 is a combine step, which combines the results of the recursive call of the procedure. So if it's your first time to meet the recursive calling of a function or of a procedure, it will be easier for you to understand the whole process of the recursion if you draw the steps of the recursive calling of the procedure. So take this example. Look at this example. If the input array has 8 elements from index 1 to index A, and if we want to sort the whole input array A, then we just need to call the merge sort procedure like this, like merge sort A 1 and 8, and 1 is the starting index, and 8 is the ending index. So within the body of this first call of merge sort, we first compute the midpoint, which is 4, and we call merge sort recursively. First, we call merge sort on the left half, which is from A1 to A4, and then we call merge sort on the right half, which is from A5 to A8. And after that, we merge the results of the recursive call of merge sorts. Then, if you want to understand what happens after you call merge sort itself, merge sort procedure within itself, then you can further draw the functions here, draw the procedure here. So the results of calling merge sort on A1 to A4 is like this. It'll further divide the subarray from A1 to A4 by computing the midpoints 2 and call the merge sort again on A1 to A2 and on A3 to A4, right? And you can make the further division by drawing out the call of the merge sort here, because calling merge sort on A1 to A2 will be compute the midpoint, which is 1, and call merge sort on A11 and merge sort on A22. Now you need to pay attention to the ending point here, because at this point, because P is R and P is 1 and R is 1, they equals. So calling merge sort and on A11 and on A22 will do nothing according to our definition of the merge sort at the first place, right? So if P equals R, then this whole procedure will do nothing and return. So that means our recursion will reaches its end at this step. Therefore, these merge sort on A11 and merge sort on A22 will do nothing, and we just need to merge the results by calling the merge procedure on A112, right? So the subcalling in this part will return after we run merge sort. And if you look at this merge sort calling on from A3 to A4, it'll further compute the midpoint between 3 and 4, which is 3, and call merge sort on A33 and A44. And similarly, they also reach the condition, the boundary condition of recursion, which does nothing at all. And this subcalling will return after we call merge procedure on A334. Therefore, this subcalling will return. So after this calling on merge sort returns, this merge procedure on A124 is called, and after that, this part is returned. And that means the calling of merge sort on A14 is fully done. And after this line is done, the next line merge sort on A58 will be done in a similar way. And eventually we'll reach the merge calling on the whole sub-area on the whole area of A. So actually I should remove the camera here so you can see. So this is the whole process of, actually it's just a part of the recursive calling of the merge sort on a short example that has 8 elements. So if we draw a tree-like structure on a small input like this, if we call merge sort on A from index 1 to 8, all the steps of the subcalling of merge sort can be visualized by a structure like a tree. As you can see, because the subarray 5, the subarray of the first elements and the second elements, they are themselves already sorted. Therefore, the merge procedure will result in a subarray of 2 and 5, which is sorted. And the subcalling on elements 4 and element 7 will result in a subarray 4 and 7. And likewise for 1 and 3 and 2 and 6. Okay, so we have one level upper above the leaf nodes as a tree structure here, right? And then we can further call merge procedures on the subarray 2 and 5, 4 and 7. If we merge these two subarrays, the resulting sorted array will be 2, 4, 5, 7. And the merge procedure calling on 1, 3, and 2, 6 will result in a sorted array 1, 2, 3, 6. And the last step is to merge the subarrays on the left and on the right here, resulting in the whole sorted array from 1 to 7 in sorted order. So this tree structure, tree plot, is just another way that is similar to the subcalling plot which we draw on the previous slide, but we just don't draw all those pseudocode. But as you can see, as we goes down to the level of recursion, the tree structure are very similar. Okay, so this tree plot is just a simplified version of the previous one. Next, another important task for us is to analyze the running time of merge sort. Because as we see, the merge sort procedure contains a recursive call to itself. Therefore, to estimate its running time, there is no very straightforward way. And actually, we first need to describe the running time of merge sorts by a technique called recurrence equation, by a method called recurrence equation. So recurrence equation describes the overall running time on a problem of size n in terms of running time on smaller inputs. And then we need to solve the recurrence equation with mathematical tools. In a more general case of recursive calling functions or recursive of procedures that recursively call itself, we usually let T of n to denote the running time for a problem of size n. So if the problem size is smaller enough, say if n is smaller than some constant c, and then we have a straightforward solution that takes constant time, which we write as theta of 1. And for n that is bigger than the constant c, then we need to divide the problem into a subproblems. And each of these subproblems is 1 over b, the size of the original problem. So here we use a and b to generally describe this more general situation. So particularly for merge sorts, a is 2 and b is also 2. But sometimes we will encounter situations that a doesn't equal b. So in this general case that we use a and b to describe the size of the subproblems, it takes T of n over b time to solve one subproblem, because one subproblem is 1 over b, the size of the original problem. And so because we have a such subproblems, then in total it takes a times T of n over b to solve a of these subproblems. After we have defined the notation of running time as T of n, and then we further suppose that it takes d of n time to divide the subproblems, because in the divide and conquer approach, we need to divide an original problem into multiple subproblems, and c of n time to combine the solutions from the subproblems into the solution to the original problem. So c of n time is for the combine step. So having these notations defined, we can write the recurrence equation as follows. T of n equals two cases. If the size of n is smaller than some constant c, then we write it as theta 1, which is constant time. And if n is big numbers, then we write it as a times T of n over b plus dn and cn. And dn is the cost for dividing the problems, and cn is the cost for combining the solutions to the subproblems. So this is a general form of writing a recurrence equations, and this equation can be solved mathematically. And actually, this is a quite general form that can be applied to a lot of divide and conquer algorithms, including the merge sort that we are going to further analyze. But it also applies to a lot of other algorithms that we are going to cover in this course. Now we will apply the general form of recurrence equation to merge sort to have a simplified analysis of the running time of merge sort. So we make some simplified assumption that the size of the original problem is a power of 2, so that each divide step will generate 2 subproblems of the size exactly n over 2. Next, let's look at the cost for dividing and combining in merge sort algorithm. So when we divide a array into 2 sub-arrays, we just compute the midpoint of the array. So it takes constant time. Therefore, dn can be written as theta of 1. And in the conquer step, because we recursively solve 2 subproblems, and each of them is of size n over 2. Therefore, a is 2 and b is also 2. Therefore, the subproblems can be written as 2 times T of n over 2. And in the combine step, because in the previous analysis of the merge procedure, we already know already know that this procedure takes theta of n time, which is linear time. Therefore, c of n is just theta of n. Okay. Having these available, then we can write the recurrence equation for merge sort like this. We just replace A and B and C and D's by the theta notations here. So as you notice, theta of 1 is a lower term compared to theta of n. Therefore, we can simplify it as the form like this. When n is greater than 1, then Tn can be written as 2 times T of n over 2 plus theta of n. So this is the equation, a recurrence equation of merge sort. And our next job is to try to solve this equation, or at least have some intuitive estimation of what Tn should be. So now let's try to obtain an intuitive solution or intuitive understanding of Tn by solving this recurrence equation for merge sort. But before that, we need to get rid of these two annoying theta notations. And what we can do is to rewrite the recurrence equation as rewrite the constant term as c, and the theta n, we write it as c times n, so that we can have some intuitive solution understanding of what mathematical form that Tn should be. And we will leave the rigid proof of this solution to future lectures when we talk about divide the general solutions to divide and conquer algorithms. But now we can just have an intuitive feeling of how we solve these kind of recurrence equations. So having this recurrence equation written like this, having c instead of theta notations, then we can write T of n like in this tree plot, and we put c times n as its root node, and on the left branch it's 1 T of n over 2, and on the right branch is another T of n over 2, because this is the form of T of n when n is larger than 1. Okay, and what we can do is to further split these child nodes. We can split the left child T of n over 2 to c times n divided by 2 plus 1 T of n over 4 plus another T of n over 4. So this is according to the definition of T of n. We just replace n over 2 into this form, and we can see that this replace is valid because we do this exactly according to our definition of T of n. And we do the same split to the right node. Okay, so maybe you will already have an understanding of what we will do. We'll further split the children node here, T of n over 4, by replacing T of n over 4 with a constant c times n divided by 4 with 2 more branches. And we want to split all the nodes that has T notations and replace it with some numbers combined by c and n, so that we will have a complete tree representation of the running time T of n. We will do the split to all the nodes until we reach the point that we can do no more further split. Okay, so after we have a complete tree plot in which all the nodes of the tree structure, there are some expressions um, using C and N and some constants, then we can just simply sum up all the numbers in the nodes of this tree, and then we can have a solution of the total running time, T of n. When we continuously divide the nodes in the tree, we will eventually reach the point where the nodes can be no longer divided. And that is when we have the smallest subproblems, and the size of the smallest subproblem is n equals 1. Therefore, when we have a complete plot of this tree structure, the bottom leaves, the number in the bottom leaves will be C, because according to the recurrence equation, the solution for n equals 1 is C. And the leaf nodes, the bottom level of the tree structure, represents the smallest subproblems. So now let's observe this complete tree structure. If we look at each level, each row, we will soon find out that, for example, for the root node, let's call it the level 0. The summation of the level 0 is C times n. And for level 1, if we go one level down, the summation is 2 times C times n over 2. The summation is also C times n. And for level 2, it's 4 times C times n divided by 4. It's also C times n. And let's go to the leaf node. Let's go to the bottom, because we can have at most n subproblems of size 1. Therefore, there is n C here, and the summation of the last, of the final, of the bottom row is also C times n. And the next question is to calculate how many levels we have, the number of levels. Once we have the number of levels, we can easily compute the total number of T of n. So the solution, the answer is, the number of levels is log n plus 1. So how do we get this number? So by simply observing each node, we can see that at level I, the number in the node is C times n divided by 2 to the power of I. So here I is 1, and for level 2, I is 2. So when it reaches the lowest level, this number should be C. And if we solve this, we can easily get that I equals log of n. And here the base of the log function is 2. Okay, so the levels ranges from 0 to 1 to 2 to log of n. Therefore, there's in total log n plus 1 levels. And now it's clear that the total running time is the number of levels times the summation of each level, which is C times n times log n plus C times n. And because C times n is a lower order term compared to this term, therefore we can ignore this term when n is big enough. Therefore, we can write the total running time of merge sort as theta of n times log n. So this is the solution to the equation, to the recurrence equation of merge sort. Now we can compare the running time of merge sort with that of insertion sort. As we have devised previously on Tuesday's lecture, we have seen that the running time for insertion sort is in the order of theta of n squared. And we just saw that the average running time for merge sort is the theta of n times log n. So in another language, that means insertion sort runs as fast as the function of n squared, and merge sort runs as fast as the function of n times log n. And as we know, n squared grows faster than n times log n. And therefore, we show that merge sort is a more efficient algorithm than insertion sort, at least from the perspective of total running time. And this difference is particularly significant when your input area is very large, when n is large enough. Okay, let's wrap up a little bit for lecture 2. So in this lecture, we use pseudocode to implement two sorting algorithms, insertion sort and merge sort. And we analyze the correctness of both algorithms using the concept of loop invariance. And more importantly, we analyze the running time using the method of T of n as a function of the input size n. And we found that for insertion sort, T of n can be written as using the theta notation as theta of n squared. And for merge sort, T of n can be written as theta of n times log n. And we have intuitively shown that we have concluded that merge sort is a more efficient algorithm than insertion sort, because the function n times log n grows slower than the function of n squared. And in the next lecture, we will give a systematic introduction to the growth of function, to the notation, to the concept of growth of functions. And we will show that theta notation is just one of a bunch of notations that can be used to describe how fast a function can grow. So that's it for lecture 2, and I hope you like this video, and I will see you next week.